So thank you very much. It's a pleasure to be here. And thank you very much for inviting me here. Let me first acknowledge my co-author from Roma Tre University, like Professor De Felice first, Davide Lavorato and Silvia Santini, and from Professor Briseghella from Fuzhou University in China, and Professor Marcello Tarantino from Modena University in Italy. We are now cooperating on this subject, and we strongly believe in the cooperation between Europe and China. My work starts since long time on this subject in about the middle of the 90s, but so we started to calibrate the Eurocode 8 design on piers, on bridge piers, on bridge in general. And at the beginning of the 2000, we supposed that it was time to take again the old piers that we tested and broke and try to retrofit them to see if retrofitting can be done in a very quick and effective manner. So the first phase was done in the mid of the 90s. The second one at the beginning of the 2000, and then there was a third phase in which we supposed to ameliorate to the retrofitting methods, because we discovered there are a lot of problems when you enter in the real retrofitting. You need some quick you need some quick method and reliable method and an effective one. So, and there are some key issues to be solved nowadays that can be underestimated from our theoretical, let's say theoretical, more or less theoretical, and which are extremely important to get good result and efficient and sustainable, as we used to say now. And finally, we have a fourth phase in which we try to use some new materials, for example, ultra-high performance concrete with mold fibers, steel fibers, in order to avoid the use of stirrups and even wrapping with carbon fiber. And this is the hope and the dream of every engineer, to cancel all the stirrups and not of all to cancel the wrapping, obviously. For those who sell carbon fiber for wrapping is a terrible future. And then we can give some, I will give you some small conclusion at the end of this history. This is Fuzhou is just in front of Taiwan. I don't have to spend any words on that. And there is a big research group, and I like to acknowledge all of them. There is no time here. We also worked in the past in retrofitting also beams, starting from shear retrofitting or using the typical shear reinforcement, but then acknowledging that it's in general we have shear and bending. So we had a lot of work and some work on shear and bending taken from real buildings. It's an old building in Rome that was retrofitted using carbon fiber in shear, and we tested the retrofitting in our lab. But then, I don't have the time to enter in any details. Then we have a second building in which we wanted to test the case, the real case that you have in a frame where you have shear and bending, and negative bending. But it is not my talk. My talk is about these columns. On the left, you can see the columns that we tested in the middle of the 90s in Italy, using and then at the beginning of the 2000s, we wanted to try to retrofit them using some, as we call now, some advanced material. In order to increase the expected life, in order to render very simple the intervention, because if you render the intervention simple, it's more safe. In general, the human error are the greatest cause of failure, and it's very difficult to deal with them. And the basic issues was to simplify the longitudinal bar substitution. Then, going to China, we wanted to compare European and Chinese code and materials in order to export our knowledge and there. And then we started to use the new material, ultra high performance, with concrete, with steel fiber, to make absolutely the same retrofitting of the piers. On the right, you can see the piers that we prepared in China. All are scaled 1 to 6. So this is the timing. We have no time to enter in this detail. And the bridges, but the case that I will deal with is this central pier of this irregular bridge, designed according to 1986 Italian code, old style, which had some obvious problem due to capacity design, because shear was very high compared to the resistance provided by the prescription at those times. And the seismic action that we used was the well-known, at least in Italy, Tolmezzo 1976 earthquake, which is very similar as response spectrum to the Eurocode 8, with a peak ground acceleration on 0.35 approximately. And if you double Tolmezzo, you get about the same intensity that you had in the Kobe earthquake in 1995. So we considered to use this earthquake as the basic reference. We use it in 1995 and 96 and 97 to test the Eurocode 8 and the Italian-style bridges via pseudodynamic. We did it in the lab, and those time not in Roma 3. I had a different lab. That period I was in a different university. And then this is what we had at the end. We had a lot of failures, especially after the second input, the highest one, the double of Tolmezzo, 0.7 G, with a response of more than 1 G at the period of the bridge, with failure, crushing of cover, and breaking of longitudinal rebars. So what we needed to do is to retrofit the bridge, to change the broken longitudinal rebars, to increase the shear strength of the bridge, and then to increase, and we had to increase also the durability we wanted. So we intended to use stainless steel for the bar substitution, the short bar substitution, just in the broken part, and to simplify the pouring, we use self-compacting concrete. The state of the art at that period was what we see here, some jacketing or some longitudinal steel substitution with FRP wrapping, as many of us have done today, have shown today. Nothing special except rebar substitution. So what we did in some PhD thesis was the repairing of these piers, removing the cover, making some injection of the core with some resin, then substituting the longitudinal bar, as you see here, with lateral welding as usual in the yard, which is absolutely terrible in theory, for a theory, but is what people do in practice. And we poured this self-compacting concrete. It was very easy, even in 2005 and 6. And then with quite no stirrups to render it simpler the pouring. without any special attention for casting concrete. And so this was the result. And finally, we provided shear strength thanks to wrapping with FRP, 3 layers of wrapping. And then we performed, instead of pseudodynamic tests, we just did some cyclic test. This is the original bridge. This is the original pseudodynamic, where we had just this pier in the lab and the rest was numerical. While for the second, what we have done, in the second, in 2005, we again did some pseudodynamic tests under the same conditions in a different lab, but the same conditions. So you can see the original bridge was this one, and then at the end it broke. The new one, after welding, retrofitting, and so on and so forth, you can see they appear quite similar, except here, where you can see something happened in this big cycle. And in fact, you will see there was some failure in the welding. And if you superimpose the two results, they should be practically the same. In theory, what we wanted to obtain, there is a difference essentially here in the retrofitting build. Okay, nothing to say about the inox steel, but except the fact that in those times, the steel, longitudinal steel inox in Italy at least, was much stronger than the original one. So the problem that what we provided in the part that we provided we replaced was much stronger than the longitudinal bars. So in the welding, the force was much higher than the possible strength on the steel. This is a big problem when you go and retrofit, even without the stainless steel, obviously. So this was what's happened when we removed the concrete of the cover. In fact, we have breakage of the welding. This was quite obvious, if one thinks so, because of the misalignment, but also because the steel was, the replacement steel was stronger than the original one. So the plastic hinge, in theory, was stronger than the basement of the steel that went in the foundation. So it was obvious that in the welding there was some overstrength required, and we had some problems. So we thought, first of all, to substitute something that guaranteed that yielding happened in the substitution part segment, which is not easy, and then to obtain some symmetric solution. And then this was what we did, but I don't want. Then in developing the work, we also find some different way of attaching the new steel, the new longitudinal steel. What I can show you is the strain in the horizontal layer of wrapping after repairing. This is these are 3 piers, and I will compare for you here. The blue one is, let's say, a pier without any substitution, anything. An original pier with longitudinal bar, as they are, with some wrapping, with no overlapping, nothing. Then the red one is a pier with the longitudinal bar without new attachment, just the original steel with some reduction of the diameter by turning, so very easy, with no problem of attachment between the new and the old. And the third one, the green one, is the first pier after breaking, let's say after the test. We cut the steel at the base of the pier, and we put some substitute rebar with opportune reduction of the diameter. So, and the number of layers for this third pier, which is the first one repaired, is 1 instead of 3. First of all, then we did in China, because this was done in China, the design according to the Chinese code, and the Chinese code is very similar to our at the end, except for capacity design for shear and for some material, but not so different. So we put some insufficient stirrups in the pier originally in order to get some interesting results. And okay, this is what we are going to compare. This is one pier, longitudinal rebar, the other with reduced rebar, 3 layers of carbon fiber. And on the 3 layers, you can see there are the strain gauges, many strain gauges. I will show you the results. And then finally, we will have this original pier repaired with some, the reduced bar are obtained by substituting segments of the steel. And here is just the stress strain behavior of steel after turning. If you turn the rebar, you obtain a totally different steel because the core is different from the outside part. So whenever you do this work, consider that the steel will be different. So after turning or after working on steel, you have to test the steel. Otherwise, you will miss totally the behavior. So this is the history that we applied, and this is the instrumentation. And this is, these are the strain gauges. I will show you just what's happened for the vertical load in red, what is in the pier with the reduced rebar under vertical load. This is the expansion of the column because it is the strain in the basic number 1 and number 2 layers of the level, let's say, of the FRP. And they are quite similar, but not totally similar. And what you can see is not perfectly vertical, the load, but that's obvious because the load is never perfect. So here you have the strain, the maximum, let's say, strain with the different level of the layers. In the case of the original pier with no reduction in the rebar and with the reduction in the rebar, and this is what you measure in the wrapping, so the enlargement of the diameter. And you can see that for the pier with the reduction, you have a concentration of deformation at the base as we want, because we don't want that it moves too much. And if you double the input, the difference is even more. But what is interesting is that at where there is the new connection between the new rebar and the old one, the strain remains smaller. And this is very important. So you have a concentration and the control of the plastic hinge at the base. And so this is the cyclic behavior, no problem. But the curvature at the base is higher when you reduce, obviously, the diameter. So this is what you see in the pier. For the original with straight rebars, you have 2 cracks, one of 12 centimeters and one 25. I remember the diameter is about 50 centimeters. While if you reduce the rebar, you have just 1 crack because you reduce the length of the plastic hinge just at the base. So what's happened, maybe we can skip the small conclusion, and then what's happened if you repair the pier, and after repairing, instead of putting 3 layers, so you cut the rebar broken, you substitute the rebar, or anyway, you substitute the rebar in the original pier with straight reinforcement, and you put reduced rebars, but instead of 3 layers, you put only 1 layer, so you under reinforce for shear and confinement. So what you can see here, these are the interior are the original pier, while the external one is the new, with small, less FRP. So what we can see is that the strain is larger, it's much larger, the double, about approximately, and if you double the intensity, it increases as well, and it's obvious because the confinement is smaller. So you expect some more damage. So this is the skeleton force displacement in the original with more reinforcement and with less. The two less are the same independently of the wrapping. Okay. Well, the difference, the real difference, is that in these latter cases you have two cracks, like in the original one. So the damage at the base of the pier is a little bit larger.
Professor Nuti, can
I finish.
Okay.
I finish. Then we changed and we did another pier without wrapping, with ultra high performance concrete and steel fibers. And what I can tell you is that the behavior of this pier was extremely good. And so we think that we can work with the dream of substituting totally the wrapping and the stirrups with this new concrete with the fibers. Thank you.